insulating uniform charge density we already know its electrical field, so I'm not going to rederive that from Gauss's law. It's a linearly increasing function up to some point, kq over r squared, then it goes down. So for insulating, it can't be hollow, of course. It has to be solid. Can't be a hollow sphere. It has to be a solid sphere or solid something, some shape. And then insulating means the charge, when you place it, it actually stays there. Kind of like a planet, a planet which has mass all throughout the planet's interior. Of course, everything we're saying for electricity in this sense is true for gravitational field. A hollow planet, you would weigh nothing in the middle of that planet, inside the interior of that planet, in a hollow planet, right? But in a solid planet, your weight would be linearly increasing as you go out until you reach the surface of the planet, which you will weigh whatever you weigh at the surface. You see. So what was the equation of that? K E is equal to KQ over R cubed R, right? Remember that it had to be continuous such that when you put little r is big R, it had to give you KQ over R squared. Then after that, it's 1 over R squared proportion. So now let's come up for an equation for the voltage of that. Right? So what function is there? Well, outside it's just still going to be 1 over R. Right? So then how about inside? So then we have to negative integrate that this time. So here's what we do. We integrate from R, from some distance R, all the way to the radius of the sphere. So we say V sub big R, which is the voltage at the surface, minus voltage at some point little r, is equal to negative integral of the E field from R to big R. So negative from R to big R, V sub big R minus V sub little r. So that's how you do it, is you first use Gauss's law to derive the E field, then you negative integrate it. So then V sub R minus V sub little r, negative KQ over R cubed, then R, so I'm going to put this function, the dr from R to big R. Okay, then we integrate that. You're going to have negative KQ over R cubed, R squared over 2, plus KQ over R cubed, little r squared over 2. Then I'm going to put here the voltage that I know at the surface. Well, the voltage I know at the surface, it has to be the KQ over the R. See, once you're at the surface of a sphere, it acts like a point charge, and then you go back to the KQ over R behavior. So then this one is KQ over R. And then I'm going to take this to the other side and bring all of this to this side. So then this one comes over here as a plus KQ over 2. And then this one cancels two of these. And you get that. And then this one comes over to the left side. And it comes as a negative KQ R squared over 2r cubed. And then this one goes to the right side as a V sub r. So that gives you the general equation for the voltage at any radius from the center. I guess we could combine these two also. And then you get V sub r is equal to 3kq over 2r minus kq over 2r cubed r squared. Okay. So let's see what kind of a function this looks like. So let's give it some numbers again. Let's say it's a 10 nanocoulomb, a sphere with a radius of 1 meter, right? So then what would the voltage be at the surface? So then it'd just be kq over r, which is 9 times 10, 90 over 1. So this would be 90 volts. 90 volts. Okay. Then after that, the voltage would decrease linearly. So if this is the radius 1 meter, and then a radius of 2 meters, what would the voltage be? Just since it's a 1 over r behavior, it'd be 45 volts, right? So graphical representation is, to me, very important to really see what is happening. You see, so the voltage goes to 45 volts, and then r equals to 3 meters. What happens? Then the voltage drops to 3, if I'm 3 times the distance away from the center as the radius, right? So then it drops by 3-fold. So then that's 30 volts. 30 volts, right? And so on. Okay, how about when I go to the center of the sphere? That's the one that we don't know, right? What's going to happen to the voltage here? For conducting spheres, the voltage was just constant, right? But for this guy, what happens when I put r is 0? V sub r equal to 0. This guy disappears and you just have this. Okay, so kq over r was 90 volts. Oh, so that means the voltage at the center is 1.5 times the voltage at the surface. So that'd be 45, 135 volts, right? So that'd be right. Oh, okay, so that's basically, if this is 45, add this to that, so graphically it looks like here, 135. So I'm adding kind of this piece on top of that piece. So it looks like this. 1.5 times the voltage at the surface. This is if the charge density is uniform, of course. Yeah, right, uniform charge density. Then how about halfway? Halfway into the sphere, what's the voltage? So then we use this equation, V sub r 3 to kq over r, kq over 2 r cubed. Let's say the little r is half of the big R. You see, halfway into the radius, I want to know, so basically at r equal to 0.5 meters. So basically you replace the little r with half r. And you're going to get 3 over 2 kq over r minus kq over 2r cubed r squared over 4. Okay, so then the r squared cancels this guy. Then you have 3/2 KQ over R minus KQ over 8R. So you get a common denominator for 4, right? So the common denominator is 8. And then 4 times 3 is 12 minus 1. It's going to be 11 KQ over R. So it's more than 1, right? So what does that come out? Well, this, in our case, this was 90 volts. So 11 over 8 times 90. So 123. Oh, okay. So on the graph, it looks, it's closer to the 135. So it's like this. So the voltage is dropping. Well, it's dropping like an inverse R squared function, inverse X squared function. So it's like this. You see? So this is 123. .75 volts. So now if you take negative derivative of this function, what should you get? The negative derivative. So right, in other words, in order to derive this, we took the negative integral of the E field that we already knew, right? But if I take negative derivative of this, you should get back to the E field, the KQ over R cubed R. So I think it does work, right? Because when you take derivative of this, this disappears. And then negative derivative of it, negative disappears. And then you just get 2R, and then the 2's disappear. And then there you have it, KQ over R cubed, and then R. So it's a quick check to take negative the derivative of this equation, and then you should get that back. So you might say, okay, that's nice, interesting. So how does that help us to know the voltage that is inside of that sphere? Well, this is kind of where it could help. For example, if I'm given another charge, let's say I place another charge over there. One nanocoulomb. So I could say, what potential energy does that charge have? What potential energy does that charge have over there, right? At the if it's a 1 nanocoulomb charge, what is its potential energy? What is the potential energy of the 1 nanocoulomb charge at the center? So if I already know the voltage is 135 and you put a charge there, how do I calculate the potential energy? Just Q times the V, right? So that's kind of literally why we're also finding voltage, because voltage is crucial to finding potential energy, right? So they're all of these are tied: voltage, electric field, electric force, and potential energy. So then what would its energy be? Well, if it's a 1 nanocoulomb charge, it'll be 135 nanojoules, right? This is a location that in Physics 101 we call unstable equilibrium. In other words, this charge here would stay there forever unless I give it a bit of a bump, because all the forces, since the electrical field that it has is 0, all the forces on it are 0, right? But as long as I don't displace it a little bit, if I displace it a tad bit to one side, what's going to happen? So it's like taking a ball and placing it slightly down the potential energy graph, right? So remember that talk in Daniel in Physics 1, potential. Remember the graphs that we made about potential energy, things like this, and then we said if we graph potential energy versus X, local maximums give unstable equilibrium and local minimums give stable equilibrium.
Yep, pretty much.
Yep, well, this is it right there. This is this kind of a point. If I put a 1 nanocoulomb charge, I'm at the top of an unstable equilibrium. So if I displace it, see, if it's right at the center, I'm okay. It's not going to be pushed to one side. But if I place it here, then of course, if I place it here a little bit, it's going to be pushed, right? So I can say, what is its speed when it reaches halfway mark? Or what is its speed when it reaches the surface? You see? So then the mass of that object would have to be given to you. Let's say the mass is 1 gram. So if I want to know halfway, after traveling halfway, what is its speed? What do I do? So you see, now you made a complete energy problem out of that. Oops. I'm trying to capture the whole thing. It's hard. Okay, so then I would say if the potential energy initial that it has is equal to potential energy final plus kinetic final, right? So the initial potential energy that it has is 135 nanojoules. So now if it's traveled halfway, what is its potential energy? What was it? 123.75, right? So you just take the voltage there times the charge that it has. So then 123.75 nanojoules plus 1/2, and then times its mass in kilograms. Okay, that's it. You see that? So now you've answered, essentially you use like ball rolling down the hill. You see? Ball rolling down the potential energy hill. So then what would that be? 135 minus 123.75. But then that's 10 to the minus 9. Times 2 divided by 0.001 square root. It's not going to be fast. Q. Okay, B final is going to be 4.74 millimeters per second. Right? So after I take the square root, if it's a small number, then I try to change it to either centimeter per second or millimeter per second. Okay, that's still not that slow. Yeah, you can see that. 4.74 millimeter per second. That's kind of how fast I believe the plates in the mid-Atlantic ridge separate, right? New material comes up, or maybe even the plates of the San Andreas Fault, the speed at which the plates move past each other. So if I wanted to know what speed they have when they reach the surface, then do the same procedure. So there, the drop will be faster, right? Kind of like a raging water slide. Here, you don't really gain speed a lot. Then it starts to glide down quicker, you see? So then here, I think you're going to gain a lot of speed because it's a it's minus r squared function, right? So it's an inverse quadratic, inverse parabola, right? So then you would just put here 90, right? Because the voltage at the surface is 90. We could even do, what if there's an open hole here? What if there's an open hole and say, ooh, this thing gets shot out, blasted off all the way to r equals to 2. You know, because as long as you displace that positive charge, yeah, it will be really blasted through like that, you know, pushed out. So what is its speed when it reaches 2? You know, so then you go all the way from here all the way to 2. Now here it's going to not increase speed as fast because it's a 1 over r behavior, right? You see that? So at r equal to 2, it's going to be 45. So depending on where you're trying to speed, of course. So that's why I like this graph. It shows you what's going to happen to that charge. I was going to say almost like ball, but you know, it's not really a ball on the track, but it behaves like a ball on the track. So then if I'm going to do the 2, so then I do 135 minus 45. Okay, then 10 to the power 9 negative times 2 divided by 0.01 square root. Oh, that's a lot faster. So by the time the charge reaches here, yeah, by the time the charge reaches here, it's going at 13.4 millimeters per second. Cool. A lot faster. Now, in electricity, there's a concept that in gravity we don't have. And that's negative charge, right? We don't have negative masses. So I could put a negative 1 nanocoulomb charge here. So what does its potential energy look like then if it's a negative 1 nanocoulomb charge? Well, then its potential energy at the center is negative 135 volts. You see that? So in other words, when I'm graphing voltage here, I'm graphing voltage based on the original charge. So I'm assuming the original sphere is positively charged. Now I can put a test charge that's positive or a negative here. So the original sphere's voltage is going to be positive, always positive, because it itself is positive. But then if I place a negative charge in its vicinity, then its potential energy is going to be negative. So then how would I plot that? How would I plot the potential energy of a negative 1 nanocoulomb charge? Then it would invert that graph, right? The graph would look like this, negative 135. Then it would look like this. And you have here 1 meter. So if at a half a meter, it would be negative and it goes like this at by 2 meters. So I'm trying to draw the exact invert, the exact inverted, and then by 2 meters it would be what? This would be 90, negative 90 volts. Here would be negative 45 volts, and then by 3 meters it'd be negative 30 volts. This is kind of how they draw the potential energy that an electron has in a Bohr atom, right? So the closer inside the n equals 1 orbit, right, the lower, the more negative the energy is. It's like that. So now that unstable equilibrium turns into a what? Right? Points of local minimum in potential energy. So it's not really the voltage that determines, it's not the voltage that determines if it's unstable, it's the potential energy. You see, that determines if it's unstable or stable. So when the charge was positive, the 1 nanocoulomb charge, okay, then the potential energy looked identical to the voltage. But if the charge I placed there is negative, it flips this graph down to the bottom. You see that? And then it makes it like this. It turns that from a unstable to a stable equilibrium. So now what's going to happen? If you have plus, 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 and then this is negative 1 nanocoulomb. If I displace it slightly to one side, what is it going to want to do? Is it going to keep going, the negative? So if it's, imagine you displace a ball and it goes up the ramp. Does it want to, if you release it, does it want to keep going up that ramp or down? It goes down, right? Yeah, so if you displace it, instead of being pushed outward, it actually goes back to that. So then it would be a different kind of question. You would say, oh, okay, if you displace it to all the way to this point, then what is its speed going to be when it gets down to the bottom? So it's kind of like everything is inverted if you have a negative charge. So if the negative charge starts out from over here, then it's going to keep going. And if there's a hole, it's going to go all the way to the bottom, all the way to the center. So it actually, not only does it do that, but it actually makes simple harmonic motion, right? If you displace it slightly, it goes back and forth. In other words, since it's kind of like a bowl at the bottom of the hill. It goes ping, ching, 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 like that. It keeps going back and forth, and of course, it has a certain speed here. We could even say, so it's going to make simple harmonic motion. Could we calculate the period of oscillation of that, or the frequency of oscillation? In other words, does it resemble a spring and a block? That's potential energy. That's a point of stable equilibrium too. A block that is stretched, its lowest potential energy is at the middle where the potential energy is 0, right? As you stretch it, the potential energy increases. And then as you compress it, the potential energy increases. So it kind of resembles the charge, a negative charge placed inside of a positive charge. And it's making back and forth motion. So what is the frequency of oscillation of that? Well, we have F equals negative Kx, which is MMA, right? So 0 is equal to MA plus Kx. And then remember the frequency of oscillation of that. So anything that is linearly proportional to the position, in other words, this displacement position, any force that's linearly proportional to that displacement position, we could use this equation that we derived back in the oscillation chapter. Square root of K over M. So the Hooke's constant of the spring, K, divided by the mass of the object, right? So in our case, if you displace it, we got, what's the force on that? It's equal to the charge of it times the electric field it has, and that's equal to Ma. The charge of it is negative 1 nanocoulomb, right? And then the electric field is what? Over there. Let's see. This one was this one was a uniformly charged thing, right? Sphere. Its electric field actually does follow that rule. It's linearly proportional to x. If it wasn't, I couldn't use that equation for omega. So it is linearly proportional, and its equation is kq over r cubed x. Kq over r cubed x. So I'm going to write that. So k big Q over r cubed x equals ma. So then we can write it like that, the differential equation, plus 1 nanocoulomb, 9 times 10 to the 9th. The charge of the original sphere was 10, was it? I think it was 10, right? 10 nanocoulombs. Yeah, 10 nanocoulombs. 10 nanocoulombs. And the radius was 1 meter, was it? Yeah, 1 meter over 1 cubed. Right, so this is the charge of the object. This is the kq over r cubed times x. So I'll put it like this. So this acts as the Hooke's constant in that differential equation, right? The k, which is the square root of k over m, right? So that is the omega in radians per second, rads per second. So there you go. That's our omega is going to be square root of this thing. So the 10 to the minus 9, 10 to the 9 cancel. That's 90 nanocoulombs. So that's my Hooke's constant, is 90 nanocoulombs. So this was just 1 cubed, so it gave us 190. That's the K. And then I have to divide it by the M of the object. So we're assuming it's 1 gram, right? The small charge, 1 gram. So then divided by 0.001. Okay, that's the omega. In other words, if I displace that, it's going to go back and forth and want to stay there. Does that bring back memories, Daniel? Physics 1?
Yeah, a little bit.
The omega square root of k over n. Okay, so now we divide that by 0.001. 0.001. We square root it. Oh, okay, so that's 0.00948868 rads per second. And then omega is 2 pi f, where f is in hertz. So this is radians per second. We say 1 radian is 2 pi cycles. So then we multiply, hold on, did I do that opposite? F is equal to cycles, 1 cycle. Oh, no, I did it opposite, sorry. 2 pi rads is 1 cycle. So if I divide, yeah, that's true. If I divide omega by 2 pi, that's going to give me the frequency in cycles per second. If I divide this by, oh, since the charge that we had was only 1 nanocoulomb, it will go back and forth, but it's going to take it a long time to go back and forth. So the frequency is very slow, right? If I had a very strong charge, then it's going to go back and forth very, very quick. You see? So this is 0.009486 radians per second divided by 2 divided by pi. So the frequency is 0.0015 hertz, or otherwise known as cycles per second. And then we invert that, we get the period, 1 over f. It's important that you guys start understanding this, because we're going to come back to this really later when we get to magnetism and when we get to AC circuits. Way at the end of the semester, you have to know frequency, period, and omega. You have to understand the relationships of that. Whenever you're discussing oscillatory motion, AC circuits, you need to know that. So then if you invert this, you get 662.31 seconds is the period. Wow, that's a long time. So that's 11 minutes. Okay, so depending on the K, depending on the charge of this that I had, depending on its radius, depending on the 1 nanocoulomb that I put there and the mass of that. So this thing, when I displace it, it's going to go back and forth. It's going to take 11 minutes. So it's going to go like this, 5.5 minutes, then come back for another 5.5 minutes. Go like that, 5.5, come back 5.5. So the whole trip will take 11 minutes, like that. Right? Cool. So that kind of gives you more of a meaning to what we're doing here. When we're plotting the voltage, we're also, in a sense, plotting the potential energy function. But the potential energy function depends on whether the charge I place there is a negative or a positive. If it's positive, then it inverts this back to the original. You see. Okay, well, what if the charge density of the sphere was non-uniform?